Today we're going to be talking about Cauchy integral formula results. Okay, so let's recall again the Cauchy integral formula from before. We now have a new way of representing the value of f at a point z. As long as we know that f is analytic in some d where the contour C resides, then we can write it like this. F of z now is 1 over 2 pi I integral around that contour of f of s s minus z ds. So before, remember, I've talked about s being an arc length segment, so a real value, but here I'm taking s to be a complex number this time around. Okay, so this is a slight change of notation. It's consistent with what the book does. So just be mindful of that this is now, s is a complex number now, so ds is also a complex differential. Okay, so again, f is analytic, and the contour resides inside some domain where f is analytic. So let's now talk about some results of this. So f is analytic means that f prime of z exists. Okay, and we can compute that now using this formula here. So actually, let's try doing that. So let's see if we can ask questions about how to represent f prime, given now we can represent f with the Cauchy integral formula. So what we'll do is actually just formally take the derivative of f and then translate that into taking the derivative of this. Okay, so of course the derivative is always gotten by doing a z plus delta z minus f of z all over delta z. Okay, and that's going to then, we're going to go 1 over 2 pi I integral over the contour of f of s of all divided by s minus, and now we're going to put in there a z plus delta z ds, and then we're going to subtract it from 1 over 2 pi I integral around the contour f of s minus z over s minus z ds. Okay, so we can write that a little bit further, and now we can write that as 1 over 2 pi I integral over the contour of f of s, and then really what we have to do here is think about this is putting this all under one integral. Okay, so what we have there is these two denominators. Of course, what we can do is rationalize this. So we're going to rationalize that, and we're actually going to get something pretty straightforward here. It's going to be oh, you know what we forgot to do is put a delta z there. Sorry, we need to put a delta z there in both of those. So there's another delta z down here. Okay, and that's because there's a delta z. I've divided by delta z everything. Okay, so what we're going to do is 1 over 2 pi I delta z integral of c, and then we're going to rationalize, and I'll skip some of the steps here. You can actually go through and rationalize this denominator just fine. I know you know how to do that. And it's going to be s minus z plus delta z quantity times s minus z. And that's all times by delta z in the numerator ds. Okay, well, you see clearly those cancel. And if I take delta z going to 0, of course we get this thing right here becomes f prime of z, which we know exists because f is analytic in this domain. Okay, and then we get a 1 over 2 pi I integral c over c of f of s. And of course, what does this turn into? Of course, when that goes away, what we see there is that becomes s minus z quantity to the second power ds. Oh, so now we have a nice formula for f prime of z. And it turns out, and I'll leave this, I won't prove all this, but we'll just state this as well. Provided we know about other derivatives, so let's say, we'll assume that f prime, double prime exists. We'll come back to this later. Assume this exists, and we actually can find, if you just do the calculation, the same calculation again, f double prime of z then equals 1 over 2 pi I times 2 factorial, which is just 2, but I'll just keep that there. Integrals over the contour C of f of s again, all over s minus z to the, drumroll, third power, right? ds. Likewise, as long as I know that some higher order derivative, I want to find the nth order derivative, and I put that parenthesis there to mean nth order derivative, and that's going to be, I can write that as n factorial all over 2 pi I, all times the integral over the contour, which lies in our domain of analyticity, of f of s all over s minus z to the n plus 1 power ds. Okay, so that's great. Now we have a bunch of nice ways of representing this function. So the question then is, so we have this nice way of representing higher order derivatives now. I'll write that down. That's going to be s minus z squared ds. Okay. We have this great way of representing derivatives, but I want to know, is f double prime, does it exist? Certainly we can write this down constructively, but I want to know, is f prime analytic? Okay, again, let's just back up here. If I have f, and I know it's analytic, and that means I can write f prime, and I know it's defined in an open neighborhood. Okay? The question then, I now have a way of computing f double prime using this formula. But the question is, if this is analytic, that means then that f double prime exists and is in an open neighborhood, just like before. And we get an enchainment. And now what we're saying then is that if f is analytic, then f prime is analytic, and then f double prime is analytic, and so on forever. And it turns out this is true, so we can write this down as a theorem that if f is analytic, then we have the following theorem that all derivatives exist and they are all analytic. So that is a very important result. So if then f to the n exists and are analytic. I should say at the point z naught. Okay, so we're always talking about a particular point. But in order to see this, all we have to do is make an observation, really. Observe that, again, we're talking about some contour. So here's the domain of analyticity for f. And we have some contour inside of it. And I've done this contour integral. And we're assuming then that of course, f is analytic inside of all of this. And inside of this is z naught, okay? And now I have a way of constructing f double prime. And note that I can put z0 anywhere I want in here. I can put it all over. In fact, I can move it all around. In fact, I can draw a little neighborhood around z0 where f double prime always exists. Since f double prime of z exists for all points in an open neighborhood, inside our contour C, then that means that f prime is analytic. Because of course f prime is analytic when its derivative exists in an open integral, which happens to be f double prime. Okay, and so of course this is we can do this by induction. F double prime is analytic, because of course I can write f triple prime as simply 3 factorial 2 pi I integral over the contour C f of s s minus z to the 4th power ds. And we could do the same argument there, and so by induction f triple prime is analytic, and so on and so forth forever. Okay, so now we know a really important fact that once a function is found to be analytic at a point, then it is infinitely analytic, if you will, or maybe a better way to state this is that all derivatives are also analytic at that point. All derivatives exist and are analytic at that point. All right, so what we need to do now is just take some more observations in here. So let's take another observation in. So let's talk about now some more results from this. And the other result we have here is that since Fn exists at a point, I should also just say if f is analytic, then all of these exist, and that implies then that the constituent functions u plus iv have smooth derivatives of all orders. And that means that uxx is continuous, uxxx is continuous, vx, y, x, y, x, y, y is continuous, and so on and so forth forever. All orders of derivatives are continuous. And so that's a nice result that comes out of this. The next thing to do then is talk about another corollary. And this has to do with what we know from Cauchy-Goursat. So remember, Cauchy-Goursat states that if f is analytic on some domain where C, this contour, and all of its and interior is a subset of D, then we know that, and I should say this is a simple closed contour, so it's a closed contour, that f of z dz is equal to 0. So any closed contour integral is equal to 0. The question then is, so this implication goes one way, but now what we want to do is, what I want to do now is say, what about the other way around? What if I know, what if I know that f of z on any closed contour in its domain of I should say, what if I know that this is 0 for all simple closed contours? what I want to be able to ask, I want to know, is it true that f is analytic? And what this is the converse of Cauchy-Goursat. Okay, that's what I really want to ask. So I want to ask that question, and it turns out the answer is yes. Okay, so the answer is yes, and it's pretty straightforward. We know from the so I can do a quick proof of this. And the idea is that, of course, we have a function. We know, be careful here, we know that the integral over any simple closed contour f of z dz is equal to 0. And I should say we should also assume that f is continuous, and that can be sussed out why that has to be true if this is true. So if this is true, then it implies that there exists an antiderivative f, capital F, such that f prime is equal to little f in D. Okay? All right, so we know also that means then that f is analytic. Right? F is analytic. And that means, and now we know from our previous results we just talked about, that means f prime, which is equal to f, is also analytic. Why do we know that? Because we know that once a function is analytic, then all of its derivatives are also analytic. And because little f is the derivative of big F, this is analytic, and of course so is f prime, f double prime, and so on and so forth. So this enchainment that started with the antiderivative, and then gave us f, and then gave us f prime, and then gave us f double prime, and so on and so forth forever, all analytic. So now we have this great enchainment of all of our logics is being put together, and we now see that this chapter on integrals is finally kind of really completed here. So we've really proved a lot of things. All right, the only thing I want to talk about is one more last piece of information. That is called Cauchy's inequality. And of course, you know that this guy Cauchy seems to have a lot of results in complex variables. Now you've got that down. So again, we're going to assume that f is analytic in some domain D, which where the contour is in D, and we'll say it's simply connected, so there's no holes or anything like that. All right, and then we have this result. Is that if we have a bound, if MR is some, I should say that CR, I'm going to call that CR, is a circle of radius R that's inside of our domain of analyticity, then if MR is a bound for f of z, where z is on CR, then if I want to bound the derivative, the nth order derivative for z on so I should back up here. I'm really talking about z naught. So CR is a circle of radius r centered at z naught. So what we're talking about is a circle like that. That's our contour. And it's at a point z naught. Okay? So we can now bound the function evaluated at z naught to be pretty straightforwardly n factorial times m r all over the radius of the circle to the nth power. And this is a pretty straightforward this is a pretty straightforward result from Cauchy integrals formula. We know that, that this is equal to 1 over 2 pi I integral on CR of f of z minus z naught all to the n plus 1th power dz. Okay, but this is a circular path, which means I can rewrite, now we can use our modulus bound. That becomes 1 over 2 pi, right, because the absolute, or the modulus does its thing, times CR of f of z moduli, and then z minus z naught moduli to the n plus 1 power dt, where dt is now that arc length segment. So we know that this right there, that's r, right? Because this radius is, for everywhere on this integral, it's going to be radius r. So we can then, and we know that this here is always going to be bounded by mr. So we can write this as follows. This is greater than or equal to mr, which we can put outside the integral. And then r to the n plus 1, because that can come outside of the integral as well, 1 over 2 pi. And then we have integral over CR dt. And of course, this integrates all around, and we get 1 over 2 pi mr all over. Oh, sorry. You know what we forgot here in Cauchy's integral formula? Our n factorial. That's by definition. There we go. That looks better. R to the n plus 1. And now this integral then, that becomes 2 pi capital R, because this is an integral around, it's this arc length circle integral. So that becomes 2 pi R. The 2 pi's cancel, and one of the r's cancel, and we get our bound n factorial mr all over r to the n. Okay, so that's our result. So now we have a bunch of results, all involving Cauchy's integral formula and a bunch of implications that really completes mathematics and our full understanding of what analytic functions are. So analytic functions have all orders of derivatives that are also analytic. So taking derivatives, you can never leave analyticity. Once you find out a function's analytic, then all of its derivatives are analytic. We have bounds on all the derivatives, and we know that all path integrals that integrate to 0 implies analyticity. So that is now a new definition of analytic functions. So we have a different way of now categorizing what an analytic function. So we have a lot of nice results. So analytic functions really comprise a host of results that are all equivalent. So now analytic functions pretty much rule the day. All right, so thank you very much.